Alright, another draft physics video presentation. Yeah, that's all. Comments and whatever is, caused, whatever the effect of the cause of reading this crap is. But anyway, we'll see what it is. I have no idea yet. That part of the script I can't read. My brain hasn't thrown it into this place where I can see things yet. So I just don't know what the script is yet. Alright, your gut feeling. So again, I'm sitting here saying, let's have a conversation about it. You present your evidence, I'll present my evidence, and let's try to be fair cops about it and say, what's the truth? Is there something else happening here? No, I'm giving you the opportunity to provide me evidence of something. You don't do it. Ask a question, you don't answer it. I mean, I'm the lawyer, and I'm saying to the other, defense attorney, I'm saying, well, here's a bloody knife with his fingerprints. What's the explanation? Go ahead. I'm listening. But anyway, all right, so it's not about a gut feeling. I'm just pointing out that this subject of drag came up. It's a real subject. It goes back to Michelson, Morley. It's connected, to the whole dissident community is in love with this whole idea of ether, and the consequence of ether is that it seems like it would have to drag things. So it's sort of an important subject. And you're just saying this is all about gut feelings and stuff. No, it's about what's the evidence. Okay, the electron slowdown isn't proof of anything. Well, I didn't argue it was proof of anything. I'm just stating, okay, that if you're going to make an argument that one thing has drag, and then you have to explain, well, if there's an example of the drag actually existing, then you can't use the argument that you haven't accounted for something that you know exists. In the sense that we all have to account for it. We have to account for why this difference. So, the alpha particles make it across. The beta particles, the helium nuclei, they somehow have perpetual motion. You can throw them into space, and they'll keep going. They'll go from one galaxy, fly all the way to the Earth. The photons will do it. The little bits. And somehow the intermediate bits, the electrons and the protons, can't do it. So there must be an explanation of some kind, right? I mean, I guess I could theorize that maybe there is enough hydrogen atoms, that maybe you could theorize that the helium nuclei somehow doesn't care about hitting hydrogen atoms much. It doesn't lose much from hitting them. Okay, it's a little bit plausible, but not very when you think about it, because it's basically a hydrogen atom hitting a hydrogen atom. So that's a little dicey. And then the photons, I could argue that hydrogen's transparent, the atoms, and the photons just go through them, and they're actually getting a little bit redshifted by doing that, but whatever. Let's see. So, and then the other guy says no shit. So again, it's a gut feeling. It's not a gut feeling. It's an argument. In the physics. So you say there's evidence that I should be compelled to believe that electrons and protons don't degrade, lose their momentum, on their own, without much help. And I'm just saying there's no obvious evidence. So, and obviously physics doesn't really care about the subject much, because I can't find anything on Google. So if anybody can find any papers or statements regarding the subject of how durable electrons and protons are in a vacuum, I'd be interested, their momentum. And what explanation there would be if you create a balanced magnetic field, how that somehow destroys their momentum, as it really theoretically shouldn't. Because we can't capture the electrons and just capture them, in a circle, and then save them, and then use them sometime later because they ran out of momentum. They just don't keep their momentum. Um, so, like I said, you can only go by the evidence. So this isn't a gut feeling thing. I certainly didn't have the same gut feeling 2 years ago. I wouldn't have said it because I didn't realize it. So, so, what's your argument? That's right. You're not making any argument. You're just saying that somehow you have a counter evidence of some kind. Well, what's your counter evidence? What's your counter explanation for how the universe works? Why don't the protons and the electrons that are no doubt being emitted by all kinds of objects in space, why don't they make it anywhere? Why can't they travel through space? All right. I mean, that's all I can do. It's just this rude crap. Yeah. Thanks. Not. These people are just so hypocritical. They somehow are striving for some higher game, and they play this low ball, and then complain. Everybody's standards are too low. All right, so Perv Action, who really needs a new name, but whatever. If we build a laser followed by a reflection maze with a ridiculous length, which I don't exactly know how that's going to help you any, but okay. One where we eliminate the amount of possible exit angles by intentionally dispersing the wrong angled light into separate chambers. See, the whole point is you can't have the light pass by any surface, so your chamber can't have a surface. And that's the whole problem, right? As soon as you have an opening of some kind, the light has to go through the opening, and that's where the electrons are hanging out, and the light's going to hit the electrons and be deflected. So you have to somehow create chambers that aren't made out of matter that has electrons surrounding it. So that's the tricky part. One where we eliminate the amount of possible exit angles by intentionally dispersing the wrong angled light into separate chambers. So you rewrote that for some reason, but okay. Couldn't we use the many angles as a kind of normalizing filter for the end product ray? I don't think so. Just because you always have this emission problem. You always have this problem that you have to build a structure around your emitter. And as soon as you do that, then you're forcing some photons to be closer to your surface and some to be further away. I would think that if you just, I would think, you keep thinking that, okay, as you go further and further away, you filtered the light because the light's diverging. So there'd be a little point that would always be pretty genuine, in the sense that those would be photons moving pretty straight if they could get to the center, over a long distance. But that would be an inevitable. I get the argument is the light isn't coming from one source. That's the problem too, right? You can't emit a bunch of light with the same frequency. Like a radio antenna has to be a certain size if you're going to make a lot of photons. You can't make a lot of photons with a little tiny antenna. So you have to make the antenna as much surface to radiate the photons as possible. And you have some regard. You have to do that to some extent with any emitter of energy, because you can't pump all the energy through one atom and have all the photons coming from one place. So you're still stuck with the problem that you can have a photon diverging this way, from one emitter, and one diverging this way. They'll end up in the same location, but they didn't get there by straight line path. So even though it looks like they're in the center, like they move from point A to point B in a straight line, they really didn't, because they're really two diverging photons. They're just diverging into each other over a longer distance. So It's good to think about. I can't say it can't happen. Um, but you're always stuck again with any filter you create. The filter can't have matter in it, you know, and that's the tricky part. It's pretty hard to make a filter with no matter in it. All right, and you can't use magnetism or something like that because photons aren't charged, so you're a little bit stuck. All right, so this other snark, what you need is evidence. Because, like I said, lots of novels were written before Einstein, okay? Even the famous one, The Time Machine. Okay, does The Time Machine have anything to do with time dilation? In what sense? I mean, it clearly has to do with the idea that speed has something to do with time, all right? I guess I would argue. But if you don't think so, fine. Okay. I thought that in novels time travel was about magically. Yes, well, I'd say Einstein's crap is magic also. You haven't demonstrated any of these bent geodesics moving anything ever. So it's just a metaphor for something everybody already knew. I'd say again, if Newton suggested gravity is caused because the fabric of empty space is really some kind of three-dimensional fabric. Well, two-dimensional in the sense that you're moving in one direction. That's irrelevant. And somehow the other two dimensions are doing something wacky. You know, the time, okay, like gravity, for example, time diverges in two dimensions. You know, and that's why we have this Lorentz transformation thing. You know, that's why time does this wacky thing where all the change is at one end. It's somehow time isn't just one dimension, it's somehow two dimensions. So when they say bent space-time, right, or they say space-time, they really mean that time is in the three dimensions. It's moving in one of them, right, like gravity would. It's moving in one, so that one's irrelevant, and it's spreading in the other two. Right? You know, so that makes sense to you? Fine. Doesn't make any sense to me. Sorry, I'm just saying. All right, not a gut feeling, just a feeling of when I take in the universe. It doesn't appear to work that way. Nothing else is doing that. Even these photons that are diverging and doing all this, you know, R squared crap, don't have the appearance of applying any magical force. Anyway, they're a real force. Okay, I thought that in novels time travel was about magically flying past the future, not by time dilation. I just don't understand exactly how it would make any difference. You're clearly taking your body going past, okay, the present. All right, so you're going fast, and you're going in sense you have to go faster than time is ticking to, you know, propel yourself to some future point where you're not being harmed by the event. You're not having to endure time. That's it. You're separating yourself from having to endure it. You know, clearly, it's no different than just going to sleep for 20 years, right? Like the old fable. You know, and you wake up one day and you say, "Oh, it's but the fact is the universe aged." Like I said, any of these time scenarios, right? None of you people are making the argument that if I propel myself faster than, if I go as fast as or up to the speed of light, that it isn't true that, again, to watch the light in the flashlight move the speed of light out of my flashlight when I'm going, say, even half the speed of light, and I watch the light leave my flashlight and hit a surface. Obviously, for the light to hit the surface at the right time, for me, for my perception, you will concede that the rest of the universe will have aged 1,000,000 years. That everything we're doing is just fine. If you go do that experiment on the moon or something, we're all going to go doing our thing. And all you really are is asleep in a way. You're frozen. The theory would be is that your metabolism is so slowed down that nothing's happening, you know, in the sense that you can perceive. It just happens. Okay, your heartbeat is, you know, 47,000 years each beat. You know, so whatever. Okay, so there's no point. Okay, I'm just saying there was lots of talk about time travel before Einstein's, and time travel based on the speed of light. So if you don't see a correlation between those two things, fine. I just couldn't care less. All right. Why electron in free space can't be shot to the moon? It's not free space, or is it? Well, that's sort of the question, right? There's so little hydrogen in a real vacuum. I mean, come on, it's really a vacuum. Pretty hard vacuum. It takes all of NASA's technology and giant, 5-mile wide nets for them to collect hydrogen to even make a nuclear furnace. That is where you don't even need much hydrogen because you're taking all the energy out, well, a lot of the energy out of the hydrogen. So even to make a nuclear furnace, they can't even come up with enough hydrogen. Even with E equals mc squared, they still can't do it. But anyway, I heard the universe is full of hydrogen atoms. Yes, I've heard the same thing, but full of means, whatever, 6 feet or something, I don't know. And also the Earth is kind of a magnet. Well, it's a kind of a shitty magnet, so you can't really make that argument. The charge of the Earth in free space, from any distance, is really lame. Okay, it's not strong at all. So if you gave your electrons any kind of velocity at all, and that's a magnetic field which degrades, by the R cubed rule, so that charge field isn't going to have much of an effect on electrons. Okay. By the way, thank you for the response. Okay, well, that's polite enough. Just saying these are open questions. Now, the interesting thing they could do, this is another one of those things, since you go to all this trouble to build this LIGO thing, and you have these very long, whatever it is, 4-mile long, 2-mile long. I mean, the part that I found hilarious was when I found out they're bouncing the laser back and forth 1,600 times. Yeah, to make it longer. Okay, so it's not hitting the mirror once, it's hitting the mirror 800 times. Well, it's hitting it 1,600 times, so they got to put a mirror on the other side too. Can't bounce the light without another mirror. But they never talk about that crap, do they? No. Well, we never hear about that part, right? So it's not even like this measurement has, it's just kind of unreasonable, right? To think that you can have that many interactions and you're not going to fuck it all up. Anyway, let's move on. Just the point. So you have this LIGO tunnel, and certainly you could see how far you could shoot electrons. But I think the more important question is, let's say there was drag, and let's say there is an ether. This might be an experiment that could demonstrate it, right? Because you could argue that the path of the electrons is going to be affected by any lack of randomness in the exposure to the field. So you can move electrons with the force. And so if the Earth was, the Earth has an absolute movement through space, that absolute movement should reveal itself in a tendency to push electrons in a certain direction. Electrons go wacky, and the whole point is they go wacky not because they go wacky, they're forced to go wacky. And so there's a cause and effect reason they go wacky. And I'm just saying, the electrons might be much better than photons for doing the experiment, because electrons will be like a laser beam. You could, like where you could blow wind and the beam would move. It's that kind of thing. So if it's true that electrons do drag, you might be able to see. The problem is, I would argue quite simply, the electrons will never make it the distance. You just won't be able to get any to go far enough where you could test which way they have a bias for, because of the ether, a bias in the ether. But let's say they aren't dragged, you'd still have to say, well, then you don't even have an argument anymore. If the electrons aren't dragged, then you're basically saying they aren't affected by the energy in space or in free space. They're not affected by. They wouldn't. There can't be any particles that are interacting with them and dragging them. That would be kind of a conclusion. But I'm just saying they don't do those experiments, right? So what's the point? I mean, it's not my fault they don't do experiments. Like, I want them to do the two-slit experiment where they put the photographic film on the sides. See, because your wave theory says this is all random. So the probability of getting a photon that does something incredibly bizarre, like it bends an insane amount, an insane amount, like 175 degrees. That's in the realm of possibility. That'll happen once a day or something. You're supposed to get one of those by your theory. My theory is saying, no, the deflection is being caused by hitting electrons. And there's no theoretical possibility that you can hit so many in a confined space. So the slit space, the amount of electrons, is basically dictating how likely you're to have a deflection that extreme. And it's not possible. The second point of my theory would be is the electrons themselves can't deflect that much. You can't hit an electron and have its momentum go sideways, essentially, and shoot another photon at that extreme angle. So clearly, by my theory, the two-slit experiment, you won't get any photons over here. Okay, the ones way out here, forget it. Electrons don't do that either. Either electrons don't do that, or you can't hit enough electrons to create that big an angle. Let's say the theory is each time you hit an electron, you move 3 degrees. You can sort of understand if there's only 10 electrons, the most you can do is 30 degrees. That's it. You can't hit more because you can't travel enough distance to hit any more. So it's not random. That's the first point. It's being created by a real thing. And so you can't get that impossible number, even though their theory, their mathematics says it's in the realm of possibility. So that would be my argument. So it's a test. Test never done. They've never been curious to go catch some of those magical photons that are supposed to be over there. They've never been curious enough to do the experiment. And so, and I get accused of being the one going by gut feelings when it seems like that's all physics is running on, is their gut feelings. And apparently their gut feeling is, Feynman really told us so when he said, shut up and calculate. Yeah, don't think, don't try to solve the puzzles. Just leave it alone, do your math. Don't think about any of the elemental or foundational assumptions. And that's pretty bad. Alright, so that's all we got. Just not much to work with, I have to say. Okay, so we do have a couple of responses. Let's see. Seriously, though, this guy's a nut job. So that's, again, something you just type on any channel on YouTube. Useless. As an insult. It's just so uncreative. Alright. If the Murlocs are really the future of the human race, Morlocks, I'd say they were the past of the human race too. I mean, when do you think we reached something called civilized? Did we ever get there? Do we have any hope of getting there? I'm just saying, what part of the human race do you think is worth preserving? What moment in time did a human being dance so well that you just have to say, oh, wasn't that beautiful? Come on. I guess Gary is ahead of his time. Well, no, there's lots of people who are a little bit cynical. But anyway, really though, it's so pathetic that he invokes H.G. Wells' novel to defend his idiotic notion that Einstein didn't contribute to the scientific body of knowledge. Now, I've never said that, so this is again another one of their resorts that you're rejecting all science because you reject what one scientist proposes. Einstein, frankly, the part they never give him much credit for, did some pretty good work in the first 2 papers he wrote on photons. Okay, this is pretty good stuff. Pretty scientific. You can figure out this whole Brownian motion thing, and you say, well, what is that really based on? And he basically proved the existence of atoms, right? I mean, that was a pretty good thing. Um, but I'm just saying, dense space is crap. If anybody else would have suggested it, they would have lost their scientific credentials, because it's just not a very productive pile of woo. I mean, to suggest the non-existent I mean, who invented virtual photon, right? The cop-out. Who invented wave-particle duality, right? These aren't people you give credit to, because this just stifles science. These wrong answers. I mean, pathetically wrong. I mean, you just know, fuck you, it's not a wave and a particle. It's just fucking stupid. Okay, it's one or the other. Anyway, to the scientific body of knowledge. So again, I never said that. So just lie. That's all you got is lies. Which by some leap of logic disputes the validity of his theories which he didn't write. So again, I didn't say he didn't write the theories. I never claimed that Einstein's plagiarized anything or stole from anybody. Now, lots of Tesla people say so. There is some dispute about some of the mathematics who really got there. On the on Mercury especially, and the math for time dilate. Those are real controversies. That the math wasn't really his. But again, I'm not disputing it on any other ground than it's a non-answer. I'm disputing the fact that you people think if somebody tells you this crap, okay, and you buy it on scant, almost vaporous, non-existent evidence. Again, the whole photon argument. You still are asserting to me that you have this absolute proof that photons are bent by gravity. Well, where is it? It doesn't make any sense. All of the galactic images are shit. They're mathematically crazy. They can't make any sense. They'll even cite dark matter as an explanation for why they don't make any sense. So now they fixed their nonsensibility by saying, well, the dark matter, and the Eddington experiment is crap. I mean, you want to say it's a great experiment, it's hard evidence, it's really brilliant proof. Why, it's not. No one shows you the actual Eddington images. Nobody shows you the evidence because it's crap. I mean, there's nothing that can be said. I mean, it's, you just go ahead and believe it. I don't care. I can't stop you from asserting things that haven't been demonstrated. And I'm just saying the theory in itself, even if photons are bent by gravity, that certainly doesn't mean that time is some two-dimensional warped thing. It's just crap that time changes in any way that could mean anything. Time can't change. The only thing you can change is your metabolism can break. Your way of functioning can break. You can be a piece of the universe that is not being affected by the forces the same way as everything else. But that's it. You can't go to some special place in some special dimension. I mean, it's just bullshit. Anyway. Alright, which by some leap of logic disputes the validity of his theories. So I'm saying the validity of his theories should be taken as individual theories. And the argument is that, yes, it was kind of wrong-headed of him, in my opinion, to think that there's any equivalence principle, that all acceleration is the same. And as I pointed out, the acceleration caused by two things banging into each other, right, means that all of the transfer of the force, okay, like especially I do it like this way, all of the transfer of the force has to go through these little locations and spread through the whole thing. Where if I move something with gravity, the force is being spread over a whole thickness of its mass, okay, and there's very little of this having to drag things along. In a sense, the little bits are being individually pushed, where for this action, the little bits aren't individually being pushed. And all of this stuff makes a difference. It's not all the same thing. And I'm saying you can tell the difference between the different ways of being accelerated. it's just demonstratable. You have to be accelerated through your feet and all this kind of stuff. You know, you could be standing somewhere, and there's a whole physics to how the motion moves from your feet, the pressure through your body. It's a real event. Okay. And then the other question is, and then you can argue, is all velocity the same? Well, I'd say that yes, once you have a velocity, then the velocities are the same. So there can be an equivalence in velocity, but not an equivalence in the form of acceleration and how effective it's going to be at moving you. So where's that lead to? I'm just trying to think of it. There's a problem. Yeah, so that's where he got this stupid idea that he has to make light do the same thing, you know, a light clock do the same thing in a ship moving as it does on the Earth with gravity. And the funny thing is when they demonstrate this, they usually use a rocket ship going up and not an elevator going down. But you know, because the deflection angles will obviously be different. You have a light clock and an elevator going down, the light's going to be deflected up in terms of how you'll perceive it. It's going to hit the wrong spot. You won't see the beam. You know, if it was a laser beam, you won't see it, you know, do some straight line to the wrong location. You know, and you won't see it. Certainly won't see it bend, because it's not going to bend its way there. It's not going to use a Lorentz contraction to get where it's going. You know, it's going to go in a straight line. The light isn't continuous. The light starts in one, like a pulse laser. You could just say it's just, you know, that's another irony, right? People think light's a wave, and yet they don't even account for the fact that the wave, you could just cut off all the extra bits, right? Just say, okay, the wavelength is really, really tiny. How does that tiny wave curve? It doesn't curve. It goes straight across the elevator. You know, it just... But anyway. So, yeah, I'm just saying that that's kind of a stupid way of reasoning, isn't it? That, okay, I'm going to invent a principle we don't need, this equivalence principle, and then I'm going to sit there and force, okay, one circumstance to look like another circumstance. So as if gravity was moving the sides of an elevator somewhere, where it's not. It, you know, it's moving the thing. Okay, how do you even say that? I mean, falling in gravity is nothing like falling in an elevator, right? I mean, but you could sort of understand that if you fell in a big silo and you had a laser beam with you, and that you started falling really, really fast, you know, we got rid of all the air and you just kept gaining velocity. We gave you a very long distance to fall. You know, where eventually you're going near the speed of light. And, you know, yeah, I think you'd understand that your laser is shooting photons, but the surface of the silo is zooming by. And that your laser is not going to hit the same location on the silo that it would hit if you weren't falling at an incredibly insane speed. I mean, why would you have this expectation that somehow it's going to bend to the original location, the still location, the location it hits when it's standing still? Somehow the light's going to go there for no good reason, because the light just wants to, because it knows somehow it has to make this theory, make this Einstein theory make sense, so somehow it has to bend to its original location where it should have hit. Come on. Stupid. Let's see. What you didn't write. Clearly someone here is not the brightest tool in the litter. Well, that doesn't even make any sense, but that's fairly rude, so you can just go fuck yourself in the ass until you're thoroughly dead. Fuck you. People with no accountability. Anyway, so I think that's it. Yeah. So I guess we'll play some video. Let's see if there's anything else in the subscription box, which frankly, like, you can't find anything you want to hit the button on. It's just so bad. Hey, look at that. Area of comparatively high energy. So that's what he's calling humans now. Yeah. we're an area of comparatively high energy. It's just funny. I mean, just how difficult it is doing this communication with each other thing, and brains seeing anything the same way. That you can agree so much with somebody, and yet they get something so obvious so wrong, and you're just like, how is that possible? How can we all know? How can we agree on all the ABCs and the whole letter thing, and then you just make up a word that has a bunch of squiggly lines in it, and you're just like, where did you get that from? How did you make all those weird? Why are you doing whatever that hieroglyphics in the middle of the word? And this is just so. How do you get there from this reasonable foundation you're standing on? It looks like every brick you laid was perfect, and there's one place where they're like, made out of cardboard. You're like, what the fuck are you doing? How do you think that's going to work? That cardboard brick. Well, anyway, I'm just trying to. I mean, it's just funny that he understands all this determinism shit. The fact that we are a byproduct, that it's all just reflexes, and reflexes are just Rube Goldberg devices. It's just we're just cause and effect, right? Cause and effect. How does that change the fact that we're actively feeling? I mean, it's a real thing that happens. You feel, you had good feelings, bad feelings. How does it negate value? I mean, the fact that we know it's a robot. Like, if I made a robot that's just like me and it feels good and bad, how does it negate the fact that it feels bad or it feels good? How do I take that and mean there's no value? It doesn't matter whether the robot feels good or feels bad. That's not important. It's not something any brain should be concerned with. It's nothing to fret about. How do you do that? How do you make suffering into a color, into a texture, into something that just couldn't matter? Just amazing to me. Nihilists are just insanely crazy. All right, let's take a break. All right, back. So I was thinking while I was gone, maybe we'll do this resonant frequency 60 symbols video. I haven't watched it yet, but the whole subject of resonant frequency, and when it comes to the difference between the different kinds of systems, like whether you're adding a force, or whether you're adding like sound or water waves, because I would argue that the distinction between the two can be revealed, perhaps through resonant frequency, and the difference in the fact that say a water wave, I would argue that this is a fact. Okay, water waves do actually provide their energy over the entire length of the wave. Okay, a little bit comes in, a little bit more, less, but it's always an amplitude or an amount over a distance. Where I would argue that things like photons don't do that. Their energy is all in one location, period, and it's just a period between the full amount, the full delivery of the energy. So there's no a little bit on, a little bit off, there's no waves in any sense. There's just a piece of energy at a frequency, and that sort of matters when you start doing this resonant thing. That is, when you're adding energy to a system, and that's what resonance really means, is having frequencies that hit, say, the simple way to illustrate it, I guess I would argue, is with like a pendulum, and you can sort of understand that there's a pendulum swinging back and forth, and the idea is you want to add energy into the system. You have to do it when the pendulum's swinging away from you, energy while it's swinging away from you, so you add it to the momentum. It's a plus. And if the energy ends up going in and hitting the pendulum when it's coming back this way, well, that's a destruction of momentum, and it'll take energy out of the system. You'll get less swing out of your pendulum. So the idea is that as this stuff bounces back and forth, and the original swing starts interfering with some other thing you put into the system, the destructive stuff will end up weeding itself out. But the whole point is that there's a net amount of energy that you will be adding or subtracting based on that frequency. Yes. And so I guess you could compare it to like our Earth orbits. If you had a bunch of moons orbiting the Earth, the theory would be that if they were going in different directions, that the destructive bits would eventually wipe each other out, and you'd end up with only stuff going one way. So as stuff goes into the gravity in different directions, they'll end up canceling out each other's. They'll interact through the constant interactions, and they'll eventually all be going one way with the net momentum of what went in originally. So it'll essentially do the math for you and figure out, well, you actually did throw more in this way than you threw in this way, and you'll end up with a system that'll end up conserving the energy in the terms of the imbalance. And it's always about the imbalance, right? More stuff going this way than that way, and that's energy is the imbalance, I would argue. But let's see what this is and such. Commercials everywhere. Sad. Physics with commercials, and a bunch, not just one. It's always more than one commercial. Eek. But this is nice that you can just ignore them, just do something else for a little while.
This is some extra discussion following our main video about Phil's homemade radio.
Right, what we got,
So that was pretty lame in a sense. Okay, so he went back to the old drawing board, made a crystal radio, figured out how to make a diode out of a oxidized penny. Okay, yeah, fun, but not very good, like getting to the physics of it.
over here, we have this wonderful crystal radio. Now, we covered a lot of the physics, but one thing we didn't really focus on, because there's an awful lot, even though this is just a few components.
Yeah, it didn't really cover the physics in terms of explaining why, okay, this is a filter for frequencies. So, but, you know, it's just this whole creating an oscillator between the storage of energy in the coil and the storage in the capacitor, and creating making those two sing the same tune or something, vibrate at the same rate.
There's an incredible amount of physics and electronics going on in this. The core of this, as well as the diode, is what's called a tuned circuit. So when I adjust this, so nothing. Now what I'm doing is I'm changing the capacitance, and that's changing what's called the resonant frequency of this circuit, the frequency at which it's most sensitive. Resonance.
Okay, so it really doesn't mean that when it's most sensitive, it just means that it's vibrating at the same rate as the energy coming in. So the energy is feeding the pendulum. It's making the pendulum swing more because you keep bringing the frequency is the same frequency. The pendulum swinging at a frequency that's compatible with, let's just say, because the harmonics will work. I mean, anything that's a half or quarter, all of that stuff will still work. But they're coming in at the same, they're hitting, the signal's coming in when the frequency is on, you know, not when it's off. I mean, but it's the pendulum thing. You can get it. It's adding energy to the system rather than taking energy from the system.
Is absolutely crucial across all physics and all engineering. It's first, second, third year, undergraduates, postgraduates, right across the board. It crops up time and time again, from everything from pushing somebody.
Right. So but that's the trick is, right? I watched the lectures and you had all this resonant stuff, and they never got to the basic point, which is, you know, and it's funny because they love this word constructive and destructive interference. They love that concept, and yet they really don't talk about that's what's actually happening with resonance, is you're just trying to avoid destructive interference and trying to enhance constructive movement. So you want the periods of the different guns are firing bullets at something, you want the bullets to hit, so the gun firing faster always ends up having one of its bullets hitting when the motion is in the right direction, and have as few bullets hitting when the motion's in the wrong direction. This is just this tipping point thing. Resonance is when you're harmonically, okay, you have two people shooting at it or pushing on it, and the net effect is they're both contributing more than they're taking away. So even though they're not pushing at exactly the same times, they're pushing more times in the same direction than they're pushing in the opposite direction.
On a swing, or a mass on a spring, I like this monkey, bumping up and down at a particular rate at its natural or resonant frequency, and that's set in this case by the stiffness of the spring and the mass of the monkey. It's a very simple equation. Similarly here, what we're doing is we're choosing a particular frequency out of a range of frequencies. This particular station broadcasts at, I think, something like, if I get this wrong, Absolute Radio, I apologize, but it's something like 1.2 megahertz.
Right, so he used the concept of resonance with one object, and it's sort of irrelevant. Yes, every object has its period. Now, the period of the monkey is set by the tension of the string, but you wouldn't say that's its resonant frequency. You'd say that's the frequency. And you're looking for another frequency that is harmonic. That is, it's going to push the monkey down further, okay, when you add it. And then you have something that's a resonant frequency, in my opinion. I mean, it's a better way to use the term, is to understand that resonance is having this compatibility thing, or this constructive interaction versus destructive interaction. And that's how I think it needs to be understood. You can add energy, or you subtract energy. You can add balance, you can balance the spring, or you can cause more imbalance to the spring. And that's what you're looking for. That's the concept.
So 1.2 million times a second the radio wave is moving back and forth. But this wire by itself isn't just picking up that signal, it's picking up all the other signals as well. So what you need to do is to narrow in and get that frequency, which is what was happening earlier. Wonderfully, we've got a mechanical, we can see this idea of resonance.
So you could understand it as you can have a whole bunch of pendulums swinging, in a row. They're all in different phases and they're all at different speeds, okay? And the idea is you want to create another frequency, another pendulum on the other side. And the idea will be is to move that pendulum along until you find a frequency where the two are harmonic, where they're moving in the same direction at the same time. And then you'll get this exaggerated height to that one pendulum will swing much higher. And so that's essentially tuning. So that's what you're doing. You're creating a noise. You have a noise in the antenna, and you have a bunch of different noises, different pendulums, and you're really just trying to find a pendulum. You're trying to scrape along that noise and see which one creates a big noise here, which means that bigger amplitude means you're on the same frequency. That is, you're hitting in the constructive way and no destructive way, the least destructive. And it's amplifying the motion of the pendulum, and therefore now you can isolate the fact that this one's going up much higher than the rest. This is a louder piece of energy, and now you amplify that louder piece.
Really straightforward. This is a very simple setup. We've got a bar, a ruler basically, and it also has its own natural frequency. We're actually
a router, a router, a router.
To drive it mechanically, there's a solenoid here and there's a magnet, so we're just driving it back and forth with a magnet. And to monitor the motion, we could look at this, but we're going to do something even nicer, which is we've got a laser pointer. That's quite neat because what we have is something that's going to tell us just how much this is vibrating.
So what's happening is the laser going down,
And there's a little
bouncing
mirror
up.
and then just bouncing off.
Okay.
At the moment, you can see it's bobbing up and down, but not very much.
No.
So we're at 4 hertz, 4.4 hertz, Brady. So what I'm going to do,
So he's just lengthening, okay, the bar essentially by having the light lengthen the bar. So instead of making the bar really long, he's just using the light because it's light, and now it won't disturb how much the bar moves. Project it, and then you can see the exaggeration, the magnification of the movement.
is I'm going to turn the frequency up. Notice I'm not driving it. The amplitude stays the same. All I'm changing is the frequency. This is really important. And okay, so it's going up, and of course the frequency is going up, so it's bouncing around a little bit more. 12 hertz, 14 hertz, 15 hertz. Okay, so we're getting some, but not much. 16, 17, 18. Now a little bit more, but not much. Still, so that's not much more than when we were at 4 hertz. That's off resonance, right? So we haven't hit the natural frequency. Remember we had the monkey and it had it. So what I'm going to do is find the natural frequency. See it building up?
Oh yeah.
All right, so he's created a pendulum, and now he's trying to find a, that's the same as the gravity, the weight of the bar, and so he's trying to maximize the weight of the bar to the vibration he's putting in terms of creating the most bounce with enough time to rebound. So he's really just going to go to the limit of the rebound speed. Right, so he's going to find a frequency that's the rebound speed.
Right? So we're at the resonant frequency, right? Now, if we go the other side of
What
it,
happened? Why is that thing suddenly going, yeah, I'm going crazy now?
because what you've done is exactly what the radio circuit is. You're driving it with the right frequency. It's got its own natural frequency. Just as the monkey on this thing or any mass on a spring has its own natural frequency, this has its own natural frequency. And now you're driving it at that natural frequency.
And what is that for?
So when he says driving, it's just you're always driving it. It's just that you're either doing it constructively or destructively, and that's all that matters here. So you're putting the energy in just when the monkey's going down, just when the monkey's going down, just when the monkey's going down. So you're compatible with the frequency of the monkey. I mean, whether you the point is that the monkey could be bobbing really fast and you could be putting your energy in really slow. So as long as you're putting your slow energy always in when the monkey is in the downstroke, you're always going to be constructive.
Frequency.
And our frequency.
So I was going to say that. So if you use a higher frequency, the odds are you're going to be 50-50. You're going to be hitting it with energy when it's going back up just as often as you're hitting it with energy when it's going back down. So the idea is to combine a low frequency with a high frequency.
Is about 25 hertz. The difference is when you're away from that frequency, you don't get much energy transfer. So it's still vibrating, but when you hit that resonant frequency, that's where you get a lot of energy transfer in.
All right, so that's all. It's just not, this is just so simple, right? It's just making sure you push the pendulum when it's moving away from you. That's all this is. And you should just say that's all that's happening. You can't put the energy in. You can't make the system have more energy. You can't make the pendulum swing wider, okay, if you're putting energy in when the pendulum's moving against you. You won't add energy to the system, you'll take energy out of the system. So the whole point is to always fire your bullet in sequence with the other guy's bullets that are hitting the thing, and your bullet hits at the same time, and maybe you'll shoot less bullets, but you're always adding energy to the wobble of the thing you're trying to knock over.
Right. And it actually acts as a filter, because if we go above that, we're now at 33 hertz. But now we're the other side and it's dying off, and you can see that it's reduced almost to what it was when we were at 18 hertz.
So you're saying when you put in the...
Right, so he's just made the two incompatible again. So you have one thing swinging, and then you push energy in, and there's going to be, and then you start changing the frequency that you're putting the energy in, you'll just go back to hitting it, when it's coming towards you.
correct natural resonance frequency energy transfer. Like, does that mean it's kind of like, to use a term you probably won't like, is it almost like the stars have aligned and this is like, yeah, the way all my structure works and my length and what I'm made of, this is just the perfect thing for everything.
Precisely.
You know.
You can do this experiment without driving it. The ruler, its resonant frequency depends on its length. So if I make this long, relatively low resonant frequency. If I make it short, higher resonant frequency. You can even hear the note changing. Resonant frequency is going down. And so if I took this now and I drove it at that frequency, I get a lot of energy.
And all that has to do with is how many atoms you have to move, right? So this is just demonstrating the fact that the energy is delayed by the process of acceleration. It has to accelerate a whole bunch of mass, and the more mass it has to accelerate, the more time it's going to take to accelerate it, period. So he puts the same energy in, yes, it's going to vibrate much quicker because there's less stuff for the acceleration to have to apply the force on. Okay, so the force is working on a lot fewer atoms. And the more atoms you have to move, the more time it's going to take, and therefore it can't possibly vibrate at the higher frequency because it can't accelerate all the atoms in the time allowed.
Transfer, and you'll get this big response. That's what's happening here, but it gets better. So we can draw a parallel between what's here and what's here. So here we've got a mass, and we've got some friction, and that's, you know, friction due to the...
See, the only part I don't like about this parallel is this fact that, okay, some waves, okay, like the wave of the wobble of that ruler, it will have an on and off, in the sense it will have more of this is happening to the actual frequency. That is, its velocity is changing with time. It moves really fast going one way, and then slows down and stops, and then it speeds up and goes back down, and speeds up and then slows down. So it's changing its velocity constantly, where obviously radio waves don't change their velocity. Radio photons.
Rod itself, but also with the air, and we're driving it with this. And what we also have is some stiffness, because the ruler's got some stiffness. Over here, we've got inductance, capacitance. It's being driven by this, by the radio waves. And what's absolutely remarkable is that the inductance here, if we write down the equations, I'm not going to do that, don't worry, Brady, but if we write down the equations, what we find is that we can do a one-to-one mapping of inductance to mass, capacitance to spring constant to stiffness, also in terms of the driving force. In this case it's a mechanical driving force, in this case it's an electrical driving force, and the equation, the differential equation you write down is identical. And this
right, because you're not having to worry about the fact that the oscillation isn't the same kind of oscillation, in the sense you're vibrating atoms in the penny. Different kind of spring, I guess you could say, but obviously those atoms would have the same. The physical atoms aren't the physical photons, so you're moving the atoms to create the electricity. This, in the sense, you're changing the atoms, so you're moving electrons. So they have stiffness where the photons themselves don't.
Solutions are identical, so that's why you see resonance here.
So I'm just saying there's a conversion inside the electronic component where you're taking the force and you're converting it to a physical vibration first, into a physical, the penny, the crystal, and but it didn't have it was different coming in. It was clumps of energy. Coming out of the crystal, it's waves of energy. The atoms are speeding up, slowing down, speeding up, slowing down, speeding. The atoms are changing their speed. The photons didn't have any change in speed. So it's just like the bullets. The bullets go into a piece of wood, okay, as clumps. The wood wobbles in this, it speeds up, slows down, speeds up, slows down. So it's changing the rules, so to speak. It's converting the clump energy into an slowly getting on, slowly off, slowly on, slowly off motion.
And you also see resonance here at different frequencies, but it's the same phenomenon.
So that moment when you got that bar to jump up and down like crazy.
So what he should have made the comparison, he should have said the bar is like the crystal. Okay, that's where I've created the wobble. That's the pendulum starting.
There is the same as the moment when you got absolute radio there.
Exactly.
Well, and there's not one frequency, is the point. So what went into the crystal is a whole bunch of frequencies. You know, that's the whole line of pendulums that's bouncing at different rates. So there's a bunch of atoms bouncing at different rates. And that's what went in. So there's a bunch of electrons communicating electric current at a bunch of different frequencies. And that's what goes into the coil and the capacitor. And those are the two things that will tell you which one's constructive and which one's destructive. Alright, so that wasn't all bad, but again, they just... if I was to relearn what resonance means, that's where I would start, is with the concept of constructive, in the sense of constructive means you're going to make more imbalance. That is, you're going to create more imbalance in the system. So now you have more motion, and you can see the more motion. And that's the idea of resonance, in the sense of recognizing its importance in terms of a system's amount of energy in a system. And that all you're trying to avoid is you putting energy in at the time when it will be a destructive interaction, in the sense you'll take two things going different ways and create a system that doesn't have any imbalance in it. You're not adding to the imbalance. Something like that, anyway. I do it differently, that's all. Because the way they do it, you don't know what they're talking about. Resonance. It's some magical property, when it's really a simple property. It just means you push down on the monkey when the monkey's going down. That's all it means. Alright, enough. Yeah, that's probably enough of a video. We'll do the Einstein video at some point in the future, because it's a lot of crap. There's crap in this thing too, where he cuts out the mirrors and he says, "Oh yeah, we've done this quantum mechanically, so maybe I'll do this," because it's I'd say it's complete horseshit. I mean, he doesn't provide any evidence of this phenomenon. Alright. I mean, no experimental evidence, like what experiment they actually did. Alright, so I guess this is the part.
Paths will still create a non-zero probability. That photon still interacts with other parts of the mirror, like for real. Even on the edges. Let's say we only have a mirrored surface on the far left edge of the screen.
So now, see, their whole theory is that somehow, okay, first that photons went here, and that somehow photons aren't going to do this angle in, angle out thing, and they're going to go over here, which there's no theory for that. So, So first they have photons that are going places they shouldn't be going. They're coming out of the laser wrong, and they're going in. Look how opposite this is. And so he's saying that they've somehow really done this experiment where they've shot light backwards on a mirror, and the light comes back forward. And I'm saying, well, you have to sort of show me where you did that experiment.
That way we're only including a spiral of canceling arrows. In that case, as you'd expect, we do not receive a photon at the black hole, unless we tweak the mirror. Let's say we know the locations where the quantum arrows point left, and we remove those sections of the mirror as well. Now the arrows don't cancel in a spiral. Even though none of the paths are even remotely obeying the law of reflection, they add up to a non-zero probability anyway.
So that says him. So, he said they did it. So
the photon can still arrive at the black hole. Classically, these situations would be called diffraction. But in quantum mechanics...
No, classically they'd be called impossible. So, what...
It's just probabilities. Mirrors violate our expectations at every turn.
They really don't, so...
Sometimes we can figure it out if we draw a ray diagram. Other times, we need to consider the wave nature of light. But in some circumstances, not even that will work. That's when we resort to quantum mechanics, because reflection is ultimately probabilistic. The point is, we didn't really understand mirrors until the last century. Don't feel too bad if your instincts
Yeah, so there was somewhere in here he says we've proven
failed you
this.
today. So do you feel like you
Okay, so let me go back even further then. I guess he said they did the experiment.
This photon exits the laser and hits the mirror. Our expectation is that the photon should obey the law of reflection. But that's not necessarily what happens. What did I tell you earlier about your expectations? Let them go. Our photon knows nothing about the law of reflection, and neither does the atom that it hits.
Yeah, it does. So, it has to be obedient to the physics. Well, anyway, just assertions without evidence is just kind of useless. So, that's what I would say. And obviously, if it's going to be another one of their, we've proven it because we did a thought experiment. Well, that's horseshit. It's like their two-slit example. Well, when we turned off the detectors that we never made and never put in the experiment, when we turned them off, something happened, right? If it's one of those experiments, then we know that it can't be relied on as evidence of anything. So anyway, so I'm suspecting the experiment from which he derives this proof is likewise easy to interpret differently. Just as the radar experiment, proof of wave interference, when no, the mathematics for jamming is exactly the same. The crappy proofs. So anyway, enough of that. All right, so we'll call it a day. Such, get about our business. Whatnot. Retiring to bedlam, actually. Probably just can't take any more. Fucking lunatics and such. So, till next time.